Hi, in this video I am going to explain about shunt voltage regulator. In my previous videos I have explained about a series voltage regulator. This is the simple block diagram representing a shunt voltage regulator. The control element will be in parallel with the load, and other than that all the elements present in the series voltage regulator will be available, or for a normal voltage regulator we will be in need of a comparator. So a sampling circuit will be there to sample the output and give it to the comparator, which will be compared with the reference voltage, and the error signal or a control signal will be coming out of the comparator, which will be fed to the control element, and the control element generates or produces a signal which controls the changes or increase or decrease in the output side or even in the input side. So we'll basically have an unregulated input V in and a series resistance here, and regulated output in this side V out equal to VL, and a load resistance RL. This is the feedback signal, this is the control signal, and this is the shunt current. And the total current input will be the summation of load current as well as the shunt current. This is the basic or simple circuit for a transistor or shunt voltage regulator. Here we'll have a Zener diode and a transistor. This series resistance RSE is connected in series with the unregulated input voltage, and the transistor is connected across your output voltage or the output side. So the unregulated voltage, if in case is decreased due to the voltage drop in RSE by a value that depends on the current flowing through the RL. So, so V out is actually the voltage across the load, and which is fixed by the Zener diode and VBE. So V out is nothing but the summation of Vz voltage across the Zener diode and the base emitter voltage of the transistor. This V out can also be written in other words, like it is the difference between V in minus IRSE, or the V in minus the voltage across the resistance RSE. So it can be represented as a summation of Vz plus Vb or V in minus IRSE also. Now we'll understand the circuit by assuming a case where if the input voltage is increasing, then there will be an effect in the output voltage. So if there is an increase in the input voltage, obviously V out is also going to increase, and when V out is increasing, VB also increases, and therefore IC and IB increases, because IC is nothing but beta IB, because this is the transistor working principle. And so as V in increases, therefore the I total current I is also increasing, causing more voltage drop across the series resistance here. Okay, this I is also changing and so increasing, so there is a voltage drop. Our VRSC will also increase, and once this is increasing, obviously V out is going to decrease. As I mentioned earlier, V out is also nothing but V in minus this VRSC. So when once VRSC is increasing, obviously V out is decreased. So the increase earlier is compensated now, or it has been controlled. Now the same happens if there is decrease in the increase input voltage also. So initially the increase in V out, there was an increase in V out. Now it was compensated, is maintained constant. Likewise, if the input voltage is decreased, the output voltage will also decrease, and simultaneously the change in the parameters of the circuit will happen, and obviously V out remains constant. So there'll be, let us assume one more case where if RL, the load resistance is decreased, because of which, for this case, output current IL will also, increase, because there is a decrease in the resistance. That's what our assumption was now. For the case 2, we assume that RL is actually reducing, or, it is decreased. So IL will increase. When there is an increase in the IL, obviously IB and IC will also change, which means it is going to decrease. And because it is supplied by this, IL is supplied by this IB and IC. So therefore input current I also remains, if we assume constant, then obviously V out is equal to V in minus VR. So it maintains the constant consistency, or it is anyway it is going to maintain constant. So if even if there is change, or it decrease in the increase in the RL happens, that is also being compensated. The limitations in the circuit are power loss. There is a considerable power loss across the series resistance RSE, and most large proportion or the most amount of the current, more amount of the current actually flows through the transistor rather than the load. And there are problems of over voltage protection in the circuit also. For all these reasons, we move on to the series voltage regulator. We prefer that compared to the shunt voltage regulator. And there is an improved version of the shunt voltage regulator available. This is the improved version of the transistor shunt voltage regulator. Here we have one more transistor connected here. The Zener diode provides a reference voltage in order that voltage across the RL senses the output voltage. And as the Vout tends to change, current which is actually shunted by your Q1 is also varied, and because of which this actually maintains your output voltage constant. This transistor Q2 will provide a larger current, which means IB, to Q1. The base of the Q1 is actually provided by the Q2, and so the regulation this regulator handles a larger load current IL. That is the most important point here to be noted here. The output voltage is set by the Zener diode, and the voltage across the this one Q2 VBE2 actually. So V out is nothing but VZ plus VBE2 plus VBE1. So this is the total output voltage summation. Thank you.